Hello, I am Václav Novotný and welcome to the tutorial of energy sources and conversions. This tutorial will be focused on thermodynamic cycles for cooling and heat pump applications. So the cooling and heat pump systems are based on left-hand turn thermodynamic cycles because in basically any diagram of thermodynamic properties, so let's say for example TS, it will be a system that will be turning into the left, and it will work in a way that it will have some heat input on one side, then you put in some work so that you upgrade the heat or increase its temperature, and you would have heat output at the other side. So you have Q in, Q out, and work input. Eventually you might get also some work output, but the work output is always smaller than the work input. Now, for these systems, or for their performance evaluations, we are using so-called coefficient of performance, where we can have coefficient of performance for cooling, also sometimes denoted as energy efficiency ratio, or ETA, which is the ratio of the what we want to get for cooling, which is the heat input, divided by what we have to put it into the system, which is the work input. Then, when it's a heat pump, so what we want to get is the heating output. So then we have coefficient of performance of heating, which is the Q out divided by the work input. Well, the work input is net work input. Most of the practical cooling systems don't have any way of recovering the work while transferring this part of the thermodynamic cycle, but if it would have, the net work input would be work in minus, of course, work out. Now the first example that we will calculate will be following. We are having some insulated area, some insulated box, let's say a big fridge, in which we have the temperature of minus 15 degrees C. Let's say its temperature inside. Then the temperature outside of the system, ambient temperature, is 25 degrees C. And the insulation is not completely perfect, so there is all the time heat flow into the system, into the compartment inside, which is 1000 watts. And now we will consider some device that will have some heat exchanger over here, and it will need to take out the heat, and by using some work reject the heat into the ambient, so that we can keep the temperature of the minus 15 degrees C. We will need to satisfy the minimum temperature difference of the heat exchangers. Which would be 5 kelvins. And for the cooling system, at first, we will employ ideal Carnot system, ideal Carnot cycle. So, how we will calculate this problem? Well, at first, we have some heat input, Q in, which needs to be removed, so it's also Q in over here. And into the cooling system is also coming some work, and it needs to be same as the heat rejected because of the energy balance. What goes in has to go out. And now for the Carnot cycle, so let's draw it in the TS diagram. And let's include also the temperatures of the ambient. And temperature inside the cooling box. Which is minus 15 degrees C. Now the Carnot cycle working fluid will need to remove the heat because of the 5 degree temperature difference at temperature lower, because the heat flows from the hot to cold. So here we have 5 kelvins temperature difference. Let's say that here will be 0.1 of the Carnot cycle, which will compress the working fluid to the 0.2, where the 0.2 again needs to be by the minimum temperature difference, 5 kelvins on top of the environment. Then there will take place the isothermal process, the isothermal heat rejection to the 0.3, from which expansion will take place to the 0.4, and then we have isothermic heat input. So just to make sure, this is the temperature inside of the box, from which we need to transfer the heat to the working fluid, and so that the working fluid can get rid of the heat, plus the energy from the compressor work also as the heat, so it will need to reject it into the environment, and the heat will flow this way. This is heat out, this is heat in. Now let's move the axis a little bit lower. So for the cycle itself, the heat input would be this area, while the area here under the curve will be the work input. And the heat input plus the work input will of course need to be the heat output, which will be all around this. So now here in this Carnot cycle we have this area to be delta S, some change in the entropy, and we can write that the heat input per kilogram of the working fluid would be temperature, let's say temperature 1 or temperature 4 times the change in the entropy. Q out would be temperature 2 times change in the entropy, and from the balance equation or from the balance model we could get that the work input needs to be the heat output minus the heat input. So for the coefficient of performance of cooling, or the energy efficiency ratio, we can write that it's the heat input, which is T1 times delta S, divided by the work, which is the heat input T1 delta S minus heat output T2 delta S. And the delta S will cancel out, so we have T1 over T1 minus T2. Now in the actual temperatures, T1 minus 15 minus another 5 is minus 20 degrees C. But of course we need to use Kelvins. And here for the work input is Q out minus Q in, so it's T2 minus T1, minus T1. So we have temperature T2, 25 plus 5, which is 30 degrees C, and plus of course 273.15, and minus T1, which is minus 20, minus 15, minus 5. Again plus 273.15, and it will end up as 253.15 divided by 50, which is the coefficient of performance of cooling, approximately 5. If we want to get the COP of heating, so then it's Q out T2 delta S divided by again T2 minus T1, the work input, so it will be 30 plus 373, which is 303.15 divided by, again, 50, and the result will be roughly 6, and you can check that it's really exactly the coefficient of performance for cooling plus 1. Now, before we move to using actual refrigerants as working fluids, let's just see what would happen if we... Now, before we move to using actual refrigerants as working fluid, let's just see what happens if we change the temperatures of the system. Let's say if we have some in the TS diagram. If we have some temperature level of the ambient, when we want very small temperature difference from the ambient, so let's say it would look like this. The temperature difference would be quite small. That means the work input would be small for the same amount of heat, which means the coefficient of performance would be very high. On the other hand, when we would go for very deep temperatures, so the temperature difference is high, the work input would be high, and the coefficient of performance would be low. Now the actual cooling system with real refrigerant is using change of the phase. So it's reverse Rankine cycle. And it looks in a way that we have a compressor. Then we have heat exchanger, which is called condenser. Following is throttling valve. And in the cooling cycle for the cold part, we have the heat exchanger called evaporator. So the heat is transferred into the system in the evaporator. Then the gaseous working fluid goes into the compressor, increases the pressure. In the condenser, the working fluid condenses and heat is released out of the system, and at the end the working fluid goes back down to the low pressure in the evaporator. Let's have a look at such system in the TS diagram. We have the saturated liquid and saturated vapor. Let's call this point number 1, where in the ideal case the point number 1 is directly at the point of saturated vapor. Let's also show here some isobars. So from the point 1 The ideal compression is isentropic, so vertical line to the point 2 over here. Following is the heat rejection in the condenser. So as you can see, we end up with the compression, at least in most of the cases, in region of such superheated vapors. So it's the superheating, then condensing, and then eventually also, based on the ambient temperature, we can get the working fluid slightly subcooled. Let's say that the ambient temperature would be over here. So we have the point 3 after the condenser and at the inlet of the throttling valve. The throttling process is isenthalpic process. There is no heat transfer with the surroundings, but there is also no work. So the enthalpy stays the same, and the change between points 3 and 4 in the TS diagram looks approximately in this way. So we get into the point 4, which is mixture of vapor and liquid, rather closer to the liquid side. The temperature 4 needs to be lower than the temperature of the area from which the heat is extracted. So in case of the cooling, it needs to be lower than the temperature in the cooling box. So for us it would be like this. As you can see, we have quite small temperature difference, so this could be perhaps case of some air conditioning. So this could be the temperature indoor and temperature of the evaporator, and then in the evaporator, as the working fluid evaporates, so the heat goes in. Here is Q in, here is Q out. We need to have the work input for the compressor, and in the throttling valve both heat transfer and the work is 0. So this was the cycle with ideal compressor and with no pressure losses. If we have the real cycle, so there are some things that make it different from the ideal one. First one, the point 1 over here, would not be exactly on the point of saturated vapor, but typically few degrees higher. It's the safety feature because for the compressor, so that it would not get liquid into it, and also it can be caused due to the parasitic heat input in the suction tubing before the compressor. So the point 1 would be at slightly superheated vapor. Then with the real efficiency of the compressor, the entropy would increase during the compression process to the point 3. Then we need to get to the pressure a little bit higher, because there will be some pressure losses. So like this. So here was point 2. Point 3 is somewhere around the same. 3 to 4 is also the same isenthalpic process. There is not much which would differ. But the point 4 should end up in point of slightly lower pressure because of the pressure drop, and that means also point of higher quality, so the cooling load will be per 1 kilogram of working fluid will be a little bit smaller. So the real cycle with pressure drops and the efficiency of the compressor would look like this. So for the cooling cycles, there are typically used pH diagrams for various working fluids, for various refrigerants. So here we can see a pH diagram for refrigerant R134A, relatively typical and especially previously used refrigerant for many applications. And now, how does the pH diagram works and what do we have here? On the y-axis, we have the pressure here in bars, and you can see that it's a logarithmic axis. So we go from 0.1, 1, 10, 100 bars over here. Then, on the x-axis, we have the enthalpy in kilojoules per kilogram. Why enthalpy is such important value in the cooling cycles is because the expansion in the expansion valve, the throttling, is isenthalpic process. So in this diagram it would be a vertical line. Then what other lines do we have here? The black one is the saturated liquid and vapor curve with the critical point in the highest place. Then inside the vapor dome we have light black line of values of the steam quality. Then the blue lines are isotherms. You can see that in subcooled liquid they are very steep. Then in the liquid vapor mixture they are horizontal lines because the evaporation and or condensation would take place at constant pressure, would take also place at constant temperature, unless it would be mixture of refrigerants with different boiling points. And then as we are going into the superheated vapor, so the isotherm actually goes down almost into the vertical line. So for example, if we would be at the saturated vapor point and we would increase the pressure, so it would be horizontal line going to higher and higher temperature. Then the green ones are the values of the unit volume, and important value for us will be the red one, which represents curve of constant entropy. And the curves of constant entropy are important for the compressor, where the ideal compressor is isentropic. So for our cooling box with the cooling cycle, we had the temperature of evaporation, the temperature in the evaporator at temperature minus 20 degrees C. The cooling box was minus 15 and 5 degrees temperature difference. And then the temperature of the condenser was 25 of the ambient plus 2 for minimum temperature difference, so it was 30 degrees C. So how would the ideal Rankine cooling cycle work in this diagram, and what would be the values of enthalpy and other parameters at important points? So let's start with the evaporation temperature. Quickly show the cycle over here. Compressor, condenser, throttling valve, evaporator, and back to compressor. We'll have points 1, 2, 3 and 4. So the point 1, we said that it would be at the steam quality to be 1, directly at the saturated vapor point, and at the temperature of the evaporation -20. So we find the isotherm -20, which is over here, and we go by this isotherm to the point of saturated vapor. So we have this point over here, this is our point 1, and we can read the value of enthalpy, which is about 385 kilojoules per kilogram. Now we will need to find the condensation temperature, which is the 30 degrees C. So again we will find 30 over here, and for that we will get point with the condensation pressure. Also for the point 1, the pressure at the point 1 is approximately something like 1.2 bars. Now the change to the point 2. The point 2 will be at pressure of the condensation, which we found over here. And which is right below 8 bars. So it's the pressure, and then the point of the entropy at the S2 is the same as entropy at the point 1. So we will go by the red line, the isentropic process, until we get to the pressure at the point 2, and the intersection will be the point 2 itself. So it's over here. We can get the enthalpy. So the enthalpy will be over here. Which is about 424 kilojoules per kilogram. And also we can see what will the temperature be. The condensation will be at the 30 degrees, but here we are right under 40, so something around 38. So now the condensation takes place, And because we are already at the temperature with the 5 degrees C beyond the ambient, above the ambient, so we cannot go to lower temperatures. Otherwise, if we could, so we would continue to the left. So here would be the point 3, and from the point 3 will take place the expansion in the throttling valve to the point 4. And it's the isenthalpic process, so it would be vertical line to the intersection with the pressure P1, and the point 4 will be over here. And the cycle will be closed. So at the point 3, the temperature is still 30 degrees C, the pressure is still the 8 bars, and the enthalpy is about 241 kilojoules per kilogram, and this is also enthalpy at the point H4, at the point 4. And also at the point 4 we can see that the vapor quality would be about 33%. Now before we continue, let's also see that we could make alternative cycle, which would condense at temperature 40 degrees C, so it would be higher. So it would have the same point 1, then the point 2 would be over here, and the point 3 would be again 5 degrees above the ambient, which is at intersection with the isotherm 30 degrees C over here, and then expansion to the point 4 would be again the same. So for this alternative cycle we have the point 2, let's say 2A is alternative, with the temperature after the compression being now higher, let's say 40, 50, about 48 degrees C, the enthalpy being about 429 degrees C, and at the point 3A, the enthalpy, as the isotherms here are almost vertical, so the enthalpy would be approximately same as the enthalpy 3 over here, so 241 kilojoules per kilogram, and that's still same as the enthalpy at the point 4. So you can already see here that you have higher difference in enthalpy for the compressor, while here you are basically at the same enthalpy. You have to end up with the same enthalpy difference 4:1, so this cycle would have lower coefficient of performance, lower energy efficiency ratio of cooling. There, however, might be reason why you would make cycle like this, and this would be to allow the cooling fluid, let's say cooling air, to heat up in the heat exchanger. So it would come at 25 degrees C. You would have 5 degrees C temperature difference, so at this point there would be minimum temperature difference satisfied. And then, as the condensation takes place at 40 degrees C, so at the nearly outlet, the cooling air could heat up to 35. So you would have much lower mass flow rate of the cooling air than in the first case. But now let's run the numbers and get the actual values. So now, just before we continue to get the parameters of the cycle, to follow the colors that we had in the pH diagram, let's change the color of the real cycle into the purple. Then this originally blue cycle will be the green cycle. Where we had the subcooling. And finally, let's draw the blue cycle, where the temperature at the point 3 was exactly at the point of saturated liquid. So let's draw the isobar. And the cycle will go from the point 1 over here, isentropically the point 2 at this lower pressure, lower the superheating, condensation, and throttling to the point. So condensation to the point 3, throttling to the point 4, and then evaporation back to the point 1. So now the parameters of the cycle. The work of the compressor is the difference between enthalpies H2 and H1, which in our case is 39 kilojoules per kilogram. Enthalpy H2 was 241 kilojoules per kilogram, and enthalpy H1 was 385. The heat rejected in the condenser, Q cond, is the enthalpy difference between points 2 and 3. So H2 minus H3 where the condenser operates between enthalpy H2 424 kilojoules per kilogram and H3 241. So the difference is 183 kilojoules per kilogram. Now the heat of evaporation is the difference between enthalpies 4 and 1. H1 minus H4 will give us 144 kilojoules per kilogram, also you should be able to get the heat transfer in evaporator from the energy balance. Here we have work of the compressor as the heat transferred in the condenser minus the work input into the compressor. So you can check that this is valid. And then the coefficient of performance for cooling is the Q in or Q evaporator divided by the work input, work of the compressor. So what we want to get divided by what we need to give into the system to get it. And we get the value of 3.692 . So per each unit of energy that we give into the compressor, we will get 3.6 units of energy in the cooling load. Now the COP, if it was a heat pump, let's say it would be heat pump operating in the winter, taking heat from the air at minus 15 degrees C, and it would be upgrading it to get again air at comfortable 25 degrees C. So in the heat pump regime, we want to get the Q condensation. We want to get the heat as the heating out of the system. And still what we put into the system is work of the compressor. And we will see that the result is 4.622, where you can see that it's indeed the COP of cooling plus 1. Now let's go for the green cycle, which was condensing at higher pressure, higher temperature, and then the point 3 was at the same temperature, and the rest of the cycle was the same. So the work of the compressor is H2 minus H1. H1 was the same, but H2 for the green case, maybe it is green. So the H1 was the same, but H2 was slightly higher due to the higher pressure. So instead of 424, it was 429. So also the work of the compressor is higher, and it will be 44 kilojoules per kilogram. Now the heat rejected in the condenser is enthalpy H2 minus H3, where H2 was a little bit different. H2 was the 429, and H3 within the resolution of the pressure enthalpy diagram, it was basically the same value as for the cycle at the lower pressure, as 241 kilojoules per kilogram. So the heat of the condensation was 188 kilojoules per kilogram. Now the heat transferred in the evaporator, H1 of the green over here, minus H4. The enthalpies were basically the same. As you can see from the TS diagram here, it should be slightly higher, but within the resolution of the system that we have from the diagram, the difference will be very small, so it will be for us still 144 kilojoules per kilogram. Now the COP of the cooling cycle, so QEVA divided by work of the compressor. Heat of the evaporator stays the same, compressor slightly higher, so from 3.6 it drops to 3.273, and COP for heating is either again from the Q condenser over work of the compressor, or we can also see that it should be value of the COP for cooling plus 1, 4.6. So it's 4.273. Now let's go to the purple cycle. For simplicity, we will say that the pressure drop will be neglected, but we will have some superheating in front of the compressor, which will be 5 kelvins, and we will have isentropic efficiency of the compressor as 75%. So with this superheating, it means that the temperature at the point 1 is temperature at the quality at the saturated vapor line plus the temperature difference for the superheating. So instead of minus 20, it will be minus 15 degrees C. Now let's get the enthalpy at this point. So we have the evaporation pressure for minus 20, but we will go into the slightly superheated vapor, so at the same pressure, but to the temperature of minus 15. So in purple, the point 1 would be over here, and the enthalpy seems to be right above 490, so let's say 491 kilojoules per kilogram. Sorry, 391. Right above 390. So H1, 391 kilojoules per kilogram. Now we will need to get point 2 before we get the point 2 after the real compression. We will need to see the point 2 after ideal compression. So let's say this would be point 2 isentropic. And we will go to the pressure of the green cycle. So pressure for the condensation at 40 degrees C, but in isentropic change. That means we will follow this red curve. And we will get to this point over here, which will be point 2 isentropic, and we get the value of enthalpy for that. Which is approximately 435 kilojoules per kilogram. So H2 isentropic is 435 kilojoules per kilogram. So the isentropic work of the compressor is the difference between enthalpies 2 isentropic and enthalpy 1, which is 44 kilojoules per kilogram. We can see that the value is same as over here for the green cycle, because it's between the same pressures, and the difference that the compression work would slightly increase as the pressure difference is realized at higher temperatures is not that high that we would see it from this small temperature difference. Now we can get the work of the compressor, of the real compressor, as work of the isentropic compressor divided by the compressor efficiency, and we will get 58.7 kilojoules per kilogram. Thanks to that, we can get the enthalpy at the point 2 as enthalpy at point 1 plus work of the compressor, which is 449.7 kilojoules per kilogram. Now let's go back into the enthalpy entropy diagram, pressure enthalpy diagram, and let's find this point 2 real. So the enthalpy should have been about 450 kilojoules per kilogram. So it's over here. And the point after the compression will be intersection of the enthalpy 450 and the condensing pressure. So it would be over here, point 2. So the compression in the pressure enthalpy diagram will look like this. Now we can see what is the temperature after the compression. So it's right above 70 degrees, about 68. Now the rest of the cycle would look fairly similar as the previous one. We will have first the superheating to the point of saturated vapor, then the condensation to the saturated liquid, and then subcooling, where the 0.3 will be the same as the 0.3 green. Therefore, also the expansion to the 0.4 will be within this diagram the same. In real, it should end up slightly left from the blue cycle. So you can show it like this, that here is 3, which is the same as the green cycle 3. And then we have the evaporation, where for the purple cycle it goes over here to the 0.1, which is a little bit further right in the superheated vapor. So after we got the 0.2, 0.3 and 0.4 are already given from before. So now we can calculate the heat rejected in the condenser. Fuel condenser is H2 minus H3. H2 was over here, H3 we had before, and we will get 208.7 kilojoules per kilogram. The unit cooling load in the evaporator, H1 minus H4, where the H1 is now over here, further in the superheated steam. The H4 remained basically the same, and we will have 150 kilojoules per kilogram. And now we can get the coefficient of performance of cooling. Q EVA divided by work of the compressor, which will be 2.557 kilojoules per kilogram. And if we operate this as heat pump, and we are interested in the heat of condensation, or heat transfer in the condenser, so it's Qcont divided by work of the compressor, which will be 3.557 kilojoules per kilogram. Now let's have a look how the temperature profiles will look in the TQ diagrams. So you will have the temperature and the heat transfer, where the heat transfer will be normalized, so going from 0 to 1, 0 to 1 for the Q, T over here, and we will have the condenser and the evaporator. So first for the condenser and the temperature profile of the air. So the air inlet into the condenser is at minus 15 degrees C. And as the heat is taken from this air, so it should actually cool down. The slope depends on what's the mass flow rate of this air. Then our working fluid. Then the working fluid is evaporating at minus 20 degrees C. And for the green and blue cycle, for the cycles without the superheating, since the working fluid is single component working fluid and the evaporation is phase change which takes place at constant temperature, so the temperature profile of the working fluid in the condenser will be a straight line. We can have counterflow heat exchanger like this. And we had specified the minimum temperature difference, 5 kelvins, to be over here. So you can see that due to the heat rejection from the air in the evaporator, the minimum temperature difference in the heat exchanger will actually be lower than the 5 kelvins, because the minimum temperature difference would be on the other side. So we should actually recalculate the cycle, where we say what is the decrease in the cooling in the air temperature in the condenser, and based on that we should actually move the evaporation pressure and the evaporation temperature lower. Now let's also see what happens if we have the purple cycle. Because the purple cycle, it had superheating at the compressor inlet, 5 kelvins. So actually the temperature profile will look like this. And what would happen? The minimum temperature difference over here would be actually 0. So the system could not work like this, and also either the superheating would need to be lower, or the evaporation temperature would need to go lower. Now let's have a look at the condenser. So we have some the air into which the heat is rejected, which is at plus 25 degrees C. And as the heat is transferred into this air, its temperature also needs to increase. Again, the rate of increase is based on the mass flow rate of this air through the heat exchanger. Now the condensing temperature of the basic blue cycle was at plus 30 degrees C. So the temperature profile would look like this up to the certain point, from which there was some desuperheating, where the desuperheating took place from the temperature of 38 degrees C. So again, you can see that we might come into trouble because the minimum temperature difference that we wanted over here would result in much smaller temperature difference at the point over here. Therefore, we had the green cycle, which was condensing at higher temperatures, higher pressures, specifically the inlet was at 48 degrees C and the condensation was at 35. So the temperature profile will look like this, where we had (35 degrees C condensing temperature, 30 degrees C the end point, and 48 degrees C the start. So the temperature difference at this point would be higher, at least by 5 degrees C. And the last case was the purple cycle, which had superheating at the compressor inlet, and then due to the compressor efficiency, the end point of the compression ended up in much higher temperature, 68 degrees C. And the temperature profile of cooling of the fluid from here would look like this. So those were the temperature profiles. And now let's have a look how much of the working fluid will we actually need. Because in our original problem we had the heat input into the evaporator. Let's calculate it with this purple cycle. So anyway, the heat input, or the Eva like this, was 1 kilowatt. So we can get the mass flow rate of the working fluid because the Qin is also the unit heat transfer in evaporator multiplied by the mass flow rate of the working fluid of the refrigerant. So from this we can get that the mass flow rate of the working fluid is the Q in capital divided by Q in lowercase. So 1 divided by 150, which is 0.0006 periodic. 0.006 kilograms per second, or also 24 kilograms per hour. So you have idea how much of the working fluid circulates in the compressor of some bigger freezer. And now what is the work input of the compressor? So the work of the compressor is unit work multiplied by the mass flow rate of the working fluid. So it would be work of the compressor 58.7 kilojoules per kilogram multiplied by 0.00666, and we will get that the result is 0.391 watts, so 391.1 watts, 0.391 kilowatts. So the thermodynamic input into the compressor is about 390 watts. If we include some electrical efficiency, eventually some frequency converter, so the electrical input into the system would be about 400 watts. So now you should be able to calculate cooling cycles, particularly the vapor compression cycles. So that's it from this tutorial.